The third type of the gear we're going to cover is going to be the bevel gears. So after the short introduction to the bevel gears, we're going to start with the bevel gears design. So the bevel gears are the gears with teeth arranged in a cone-shaped manner. So it's not straight, it's not just helix like the case of the helical gears. It's mainly going to be arranged in a cone shape, and it can be straight or it can be helix, as you can see from these images. The types can be straight bevel gears, spiral bevel gears, the zero spiral bevel gears, and the hypoid gears. So in figure 822, we can see that we have straight bevel gears, we have the spiral bevel gears, we can have the zero spiral bevels, and we have the hypoid. In addition, we have the straight bevel gears. That's what you can see as an image in the figure E. And the main components that we are going to have for the gears is going to be shown here, like where we're going to have the outer cone, where we're going to have the face width, the angle alpha, we have the center of the gears, and the pitch diameter location. It was mentioned before that the main advantages of the bevel gears are going to be the right angle drives, so it can change the direction of the rotation by 90 degrees. Also, it's going to provide a low noise and vibration. The main disadvantage is that getting the axial load, which is going to be a complicates the bearings and the housing selection. So the geometrical features of the straight bevel gears as shown in the figure A22 are explained here. What is the dimension and what will be the required formula to calculate it. So this actually can be a good reference for you when you're going to start to make a design for the bevel gears in the example we're going to have here. So first we need to understand what are the forces we have on the straight bevel gears. So mainly because of the conical shape of the bevel gears and because of the envelope tooth form, we have three component sets of the forces acts on the bevel gears teeth. So using the notation similar to that for the helical gears, we will compute the tangential forces, the radial forces, and the axial forces. It's assumed that the three forces act concurrently at the midface of the teeth and on the pitch cone as shown in the figure 810. Although that the actual point of the application of the resultant force is a little bit displaced from the middle. No serious error will result if again to consider it to be exactly in the middle. So starting the calculation of the forces on straight bevel gears, first we can calculate the torque by knowing the power and the RPM value. So the torque can be computed from the equation 1010. If I know what the power is, multiply by 63,000 and divide by the N in RPM. The power here in horsepower is not in kilowatt. You have to remember that. Now, then you are going to using the torque, and you're going to use the pinion, for example, for the transmitted load to be calculated. So we're going to use the torque has been calculated from the equation 10 and divided by the radius to find the force, tangential force of the pinion. The Rm is the mean radius of the pinion, and the value of the Rm can be computed from the following equation. The Rm is going to be equal to diameter divided by 2 minus the face width divided by 2 multiplied by the sine of the gamma. Remember that the pitch diameter d is measured to the pitch line of the tooth at its large end. And that's what we can find in the figure A22 that we presented earlier. Further, the angle gamma is the pitch cone angle for the pinion, as shown in the figure A10. The radial load acts towards the center of the pinion, perpendicular to its axis, causing the bending of the pinion shaft. Thus, the WRP is going to be equal to the tangential force multiplied by the tangent of phi, which is the pressure angle for the teeth, multiplied by the cosine of gamma, which is the pitch cone angle for the pinion. The axial loads act parallel to the axis of the pinion, tending to push it away from the mating gear and produce a bending moment on the shaft. Thus, Wxp is going to be equal to the Wt, the thrust load, tangential load, multiplied by the tangent of phi, multiplied by the sine of the gamma. So to start the calculation, we need to collect some of the data. First, what is the power to be transmitted? Second, the type of the driver and the driven loads. The speed of the driving gear, the center distance, the speed of the driver gear or the velocity ratio, and other information related to the problem specification. The design hypothesis will be, first, the gear teeth should not fail under the static loading or dynamic loading during the normal running conditions. Also, the gear teeth should have a wear characteristics so that their life is going to be satisfactory. We also need to use the space and the material to be economical. The alignment of the gears and deflections of the shafts must be considered. Finally, the lubrication of the gears must be satisfactory. So the procedure can be summarized as the following steps. The first step is specify the design data, transmitted power, the input and the output speed, the center distance, the type of the driver and driven load. Then we can choose the overload factor from the table 9.1, depend on what will be the power source and what will be the driven machine. We can simply compute the design power in that case to be the actual power multiplied by the overload factor. So after we found what was the value for the design power, and we can simply calculate what will be value for the PD or the module M from the figure 911. So once again, we explained this one earlier, but we need to know what will be the pinion speed in RPM. Then we go to the design power. If we're going to go to the right side y-axis, we can use the power in kilowatt. And if we're going to go to the right, to the left y-axis, we are going to use the power in horsepower. So simply just decide what would be the pinion speed according to the specification of your design, intersected with when any of the lines based on the power, and then simply you can find what will be the PD value or the M value for your system. The second step is specifying the number of the teeth for the pinion. And this can be anything from the range of 17 to 20 teeth. So we can simply compute the nominal velocity ratio, the VR, compute the approximate number of the teeth for the gear. We can compute the actual velocity ratio. We can compute the actual outward velocity. We can compute the pitch diameter, the face width, the pinion mean radius, the gear mean radius, and finally the baseline speed. With that, after finding the VT, we can simply calculate using the power and the radius, torque and the radius, we can calculate what will be tangential force that we can transfer to the step number 3. So after calculating the tangential force, we can start the analyzing of the gear tooth failure mode. First, we start with the root and finding the bending stress number. Also, for the surface, we can find the contact stress number. So we need to find the values for the factors as we are going to showing in the next step. So in step number 4, we start to specify the type of the material for the gears to find the elastic coefficient CP. So for example, if we're going to have the 2 steel gears, we can simply check the steel, the first line, and we're going to intersect it with the third column. So we can find that 2,300 psi. So we need to take that to the under square root. You can read about details about how to use this one from the description of the table below. Step 5 is to specify the bending geometry factor J for a 20-degree pressure angle and 90-degree shaft angle from the figure 1015. So what you can see in this graph is first we need to find what is the geometry factor. We can find that in the x-axis. For this diagram 1015, figure diagram 15, you can simply know that the shaft angle is 90 degree and the pressure angle is 20 degree. So what we need to know is that number of the teeth for the gear in which the geometry factor is going to be desired. That's what you can find in the y-axis. In the top x-axis, we can find the number of the teeth in mate. So by selecting any of those curves, simply by finding the intersection between the y-axis and the top x-axis, we can find the value of the geometry factor in the lower x-axis. In step number 6, we can specify the pitting geometry factor I for a 20-degree pressure angle and 90-degree shaft angle from the figure 1019. Now we are going to do the same thing. We need to know what is the number of the teeth in the pinion, and we're going to intersect it with the number of the teeth in the gear. After we do that, we can simply find what will be the value for the geometry factor from the x-axis. Step number 7 is specifying the size factor from the table 9.2. So once again, we need to decide what will be the diameter of each value. Is it going to be more than or equal to 5, or is it going to be anything less than 5 down to 1.25? So we can find what will be the value for the KS based on the metric module M, and the size factor then can be found. You remember that we found the M from the first step of the calculation. The 8th step is to specify the load distribution factor Km. And this can be done either by using the figure 1014 or by using the equation. The equation, first you have to specify what the value of the Km be, and this will depend, of course, on the gear straddle mounting. It's either going to have both gears straddle mounted, or one of them is going to be mounted, or neither is going to be mounted. So based on that, choose the KMB, then you multiply it by the face width square multiplied by 0.036. Or simply, if you know what the face width is, what is the straddle mounting, and then you choose one of the curves that we have on the figure 1014, do the intersection, and you will find the value for the Km. So as we learned earlier for the spur gears and the helical gears, the same thing is going to be done in the step number 9 for the bevel gears. You need to specify the quality number, and this can be done from the table 9.5. So depending on the application, we can choose what will be the quality number. So it can be 11, for example, for the cement mixer drum drive, or it can be A2 for the gyroscope. So based on that, we can select the value that's required, and then we're going to move to the next step. So in the step number 10, we choose the material for the pinion and the gears. And we can use the value for the SAC or this SAT from the figure 918 and the figure 919 with the table 9.9 and table 9.10 and the table 9.14. So depending on the steel type, you can decide what will be the value for the allowable bending stress, which is the SAT. And you can also find from the figure 919, you can find what the value for the allowable contact stress in megapascal. So you can find in KSI or megapascal depending on the units you're going to use for your calculation. Also, we can find the equation actually to do that the same way, and depend on the grade of the steel. I think that the notebook also have further figures with the different types of the material that you can select for your design. So if you prefer to use the tables instead of the graphs for the step number 10, you can choose the table 9.9, 9.10, and the 9.14. So for the 9.9 is going to be the lowest stress for the case hardened grade 1 steel material. The 9.10 is going to be the lowest stress number for the iron and the bronze gears. And the 9.14 is going to be the approximate allowable tool bending stress in the plastic gears. Most of you may contain his career or even his study doing the mechatronic engineer as need to design the plastic gears. So I think the table 914 is going to be quite useful for your future projects. Continue with finding the factors. The step 11 is going to be about the dynamic factor KV. And the KV have the equation to be used. Okay, we need to specify the U value from the next equation, the KZ value from the third equation, 85 minus 10U. And if the U is going to be negative value, then you are going to use the value of the U to be equal to 0. And thus, the KZ, for example, is going to be 85. So for checking the value for the KV, it must be greater than the KV minimum, which can be calculated with the equation of the 2 divided by the n multiplied by the tangent inverse of the VD divided by 333. If it's not, then simply a higher quality number should be specified. So you have to know that the calculation of the inverse tangent must be in radian, not in degree. So for the equation for the KV minimum, you should use the VT divided by 333 as a radian, not in degrees. Step number 4 is specify the safety factor. And this typically going to be in the range of 1 to 1.5 or 100 to 150%. The hardness of both the pinion and the gear are nearly equal to enable each to withstand the contact stress without pitting, allowing the use of the hardness factor, which is CH, to be equal to 1, and not including that the factor in that equation. So to specify the reliability factor is going to be next step, and this can be done by using the table 9.5. So the value for the KR or reliability factor depend on the safety factor, and this will be anything like, for example, again, to have reliability of 0.9, which is one failure in 10, it's going to be 85, and it's going to be up to one failure in 10,000. I'm going to take it to be 1.5. So step 13 is going to be specifying the stress cycle life with the YN, and this can be done by using the figure 921. So first you have to know what is the recommended design life for your application. So again, we can have the table 912. 912, we can see that we have either domestic appliances, which can be last for maximum 2000 hours, or we can have critical equipment in continuous 24 hours operations, like for example the power plant, and thus the design life recommended is going to be anything between 100,000 to 200,000 hours continuously. So by getting the value for the design life H, we can simply go to the figure or using any of the equation that we have there to calculate the value for the YN. So the NC in the equation is the number of the loss cycle. Okay, and we can put in the equations that we have there, depending on what the value that we're going to have for the material. And we are going to be able to find what will be the value for the stress cycle factor we're going to use in the further calculations. Again, the pitting resistance stress cycle also can be calculated or can be found from the figure 922. And again, this will depend on the recommended design life. So, of course, the number of the cycle can be found according to the recommended design life. So again, we can use the equation depend on the material, and also we can simply just use the figure by intersecting the number of the loss cycle with the Zn value, with the curve, sorry. And then we're going to find what will be the value for the stress cycle factor, Zn. Now, the final step is going to be when the factors CO, CV, and the CM are the same as the KO, KV, and the KM. And we can use the value for the CO to be 0.634. And this will allow the use of the same allowable contact stress as for the spur and the helical gears equations. So we can check if the selected material satisfies the following design conditions. And if not, simply just select a new material and repeat the calculation as a new iteration again to find out that the value of the stresses are going to be less than the allowable stresses material, and the same thing for the contact stress is going to be less than the allowable contact stress for that material. So that's it. This will be the calculation we can use for the bevel gears. We didn't include an example in the tutorials because actually the helical and the spur gears are quite more important now, but you can find an example available in the notebook and you can go through it, or we can go through it with you later. I can make a video and we can explain the steps and how to apply these steps for you. So the next video is going to be about the worm gear design, and once again we're going to have first introduction about the worm gears, and then we're going to have the calculation, the design procedure for the worm gear design.